Hi, I'm Joshua Lee, and in today's video, we're going to be learning about circuit components, specifically the resistor and the capacitor. If you haven't watched my last video, you should see that first because we're going to be using some of the concepts that we already learned. We're going to be talking about what resistors and capacitors are, what they're used for, and why they're important. Let's start off by talking about the resistor. Electricity works a lot like water in a pipe. Let's say there's a pipe, but there's a narrow section in the middle. If this section is narrow, then any water flowing this way will encounter resistance and will be forced along this narrow path. Then the water would encounter resistance, which is exactly what a resistor does to electrons. A resistor is the most basic circuit component, and it has a simple purpose: to provide resistance. Although resistance blocks the flow of current, it's not always a bad thing. For example, a resistor could be used with a sensitive component such as an LED. You don't want too much current flowing through it or else it will burn it out. But you don't want too little current because then the LED won't function properly. A resistor would allow you to control the current and tune it so that you get just the right amount. A resistor is one of the most versatile circuit components, and this is just one of its many uses. Another use for a resistor would be heating. When electrons try to pass through something with high resistance, they constantly crash into atoms in the object. Remember that energy cannot be created, but only transformed into other forms. So when electrons crash into the atoms, their kinetic energy is converted into heat. Circuits often take advantage of this fact in everyday life. For example, toasters use this mechanism. Their wires are specifically designed to have high resistance so that they can generate heat and toast your bread. Certain resistors, called variable resistors, allow you to change their resistance, usually by turning a knob or sliding a slider. This allows you to control the magnitude of specific circuit functions. Some examples include the volume of an amplifier, the pitch of a musical tone, speed of a motor, and the brightness of a lamp. The most common resistors are carbon film resistors, which look like this. You may notice that there are three colored bands next to each other and a fourth band that is slightly separated from the other three bands. The first three bands represent the resistor's resistance. The fourth band represents the tolerance. The tolerance is how much the margin of error is, or how much the actual resistance can differ from the intended resistance. Usually, a lower resistance is better since it gives you a better idea of how much the resistance actually is. Now let's learn about the color code. Here I put the code into a chart. Using this chart is simple. First, you get a two-digit number by comparing the resistor's first and second bands to the chart. For example, if the first two colors were orange and green, your two-digit number would be 35. Then you multiply that number by the factor that your third color represents. If my third band was brown, then my number would be 350. This is your resistance in ohms. Now look at the last band. Most of the time it will be either gold or silver. If I had a gold band, my resistor would have a value of 350 ohms plus or minus 5%. So let's look at how resistors are made. So how are resistors made? In the case of carbon film and metal film resistors, there's a ceramic tube in the middle. And then this tube is coated with carbon film or metallized coating if it's a metal film resistor to a certain thickness. By controlling that thickness, people can control the resistance of the resistor. You can also tune the resistance of a resistor by cutting a spiral into it. Then this creates a path for the electrons to follow. Let's say there's two resistors. If the spiral is wide, then the path will be shorter, meaning less resistance. If the spiral is close together, then the path will be longer. So that means more resistance. After that, they put caps on the ends with leads on it. Then they dip this middle part into a lacquer coating. which is how a resistor is made. By the way, the symbol for resistor is this. It looks like a zigzag with leads. Let's move on to capacitors. Capacitors, just like resistors, are very useful. Let's say there's a pipe with a valve on it. If you leave the pipe on, the water will constantly flow, and if you turn this valve off, then the water will immediately stop flowing. If we go back to our water example, a capacitor would be like a water tank that slowly fills up. So this would be a pipe, and there's a tank here. There's a pipe that flows out. So this would represent the capacitor. Let's say you have a valve here. If you leave the valve on, the water will constantly flow here until it fills this tank up. Then, even if you shut the valve, there will be a slight delay until the water stops flowing out of this end. Unless you completely drain the tank, there will be a steady flow of water coming out from this end. So, if you turn this valve on and off repeatedly, then from here, it will just look like a steady flow since the water keeps filling and unfilling in the tank. So, capacitors are often used as rectifiers to smooth out any interruptions from the power supply. A capacitor's job is to store electrical charge a bit like a battery, but unlike a battery, it stores charge in an electrical field and not as a chemical. It can't store as much energy as a battery, but it can charge and discharge energy much faster than a battery can. This is incredibly useful. So capacitors are often used as rectifiers to smooth out any interruptions from a power supply. The symbol for capacitor is this. It represents two conductors on either side of an insulator. Let's try connecting a capacitor to a battery. The symbol for battery is similar to a capacitor, but there is one positive end and a negative end. The positive end is longer. If we connect the battery to a capacitor like this, then the electrons from the negative end will keep flowing into one side of the capacitor. The electrons on the other side of the capacitor will then flow to the positive side of the battery. The electrons on this side of the capacitor can't move on to this side since there's an insulating material in between. After all the electrons flow across, there will be no more current flowing, and that means that the voltage across the battery will be the same as the voltage across the capacitor. Then, if we take this capacitor and disconnect it from the battery and connect it to an LED, let's say this is an LED, there will actually be current flowing. Then the electrons from this side of the capacitor will go around to this side. This will only last a short duration though. Once the electrons are balanced out on either side of the capacitor, the voltage will become zero and there will be no more current flowing. In today's video, we learned about capacitors and resistors. In the next video, we'll learn about two more circuit components. I hope you stay tuned for that video too. Thank you.